Okay, so one thing that the slides of the last lectures of last week and the week before, they are on the webpage of the class. I just, uh, uh, they were there, but I guess I also saved them with the wrong preferences or whatever. They were not downloadable. Now they are downloadable. So they're there. I also put there already the ones for this class and the next. So everything is there. And I'll still be posting some papers and stuff which I haven't done yet. I want to add a few more references there for available. Okay, so yeah, let me just get on to the next few things that I want to discuss. So here's where we are so far with what happened in the last couple of weeks. So we have these are the main that we got down. So at this point, so syntactic objects are these three non-associative commutative magma generated by the set of lexical items and syntactic features. Workspaces are the commutative of algebra, commutative graded connected of algebra of binary rooted forests, whose components are syntactic objects. Merge is a Hopf algebra Markov chain over this Hopf algebra. And this minimal, what is called minimal search, is a grading of the coproduct that selects as leading order terms the external and internal merge. The sideward merge, which is subdominant for this purpose of structure formation, is needed for the Markov chain property. So that's how these things relate. And the minimal yield and constraints on size of workspaces can be derived from the algebra grading from as this kind of complexity loss principle that I described. What is referred to as countercyclic movement, the kind of things like late merge. They are the insertion Lie algebra that is dual to the Hopf algebra. So the primitive elements of the dual Hopf algebra with the Lie bracket coming from this insertion. And the last thing that I was discussing last time is there's more refined. So no, this is up to this is just the part that has to do with structure, with free structure formation, in the sense that this generates all the possible structures. And then after you have this structure generating process, you have to start to introduce various kind of filters for which structures are that are generated by this free mechanism are viable or not. And so there's some criteria of viability that are largely language independent. And so you have these first kinds of filters which have to do with the possibility of having a head function on your structures. And with these labeling phases and labeling, so heads and complements, and the structure in sub-nested phases, and the corresponding labeling with a well-defined labeling for the internal edges of tree based on this projection of head. And okay, these were the first constraints that I was discussing last time. So I will say a few more about some of these general kind of constraints that are not specific to embodying in one particular language, so not language specific constraint. And then I'll talk about what happens to the more language specific kind of constraints that one needs to impose. Okay, so externalization is what refers specifically to all the constraints that are that have to do with the learning of language. So that have to do with this, having to deal with one specific language and constraints that come from the learning of one specific language. But these more general aspects that are still, in a sense, prior to externalization, like heads and complements and so on, include also a couple of other things that I haven't discussed yet. One is what in linguistics is usually called Theta theory. Theta stands for thematic roles. And of course, in every language, one encounters this kind of thematic roles. Like, there's know, it has again to do with the structure of certain mandatory relations, like between head and complement. And it's the kind of roles that are often embodied if a language has noun declension. It's often embodied in the kind of cases that you have something is a dative, a genitive, and an accusative. It's a particular kind of role that it has with respect, usually with respect to a verb or with respect to a predicate. That's the center of that structure. And I'll discuss with you that this in this mathematical setting that we're using for modeling the construction of syntactic structures, this can be phrased in terms of a structure of operad and of column operad in particular. And also, I also want to say a couple more words on something that I mentioned this time. So I mentioned this form set operation by which you can group together a certain number of syntactic objects as being in a related structure, which is used either for this unstructured sequence formation, but also to mark certain things together by being identified as copies, so by restricting to certain diagonals. And I'll discuss that too in this setting, which in linguistics, it goes under the name of obligatory control. And okay, so let me just recall a few preliminaries that some of which I have mentioned already last time, because I was talking about head and complements and modifiers. These are the elements that we have seen in forming the phases in the structure. So in a sense, the head, from the linguistics perspective, is that lexical or phrasal element that is essential for the forming of that phrase. That if you remove it, the phrase will just fall apart. The complement is phrasal elements that the head must necessarily combine with for the structure to be standing. So, for example, you have verbs that call for a direct object or an indirect object, or some kind of complement, other forms of complementation. And a modifier is whatever you have as part of your other phrasal elements, which are not necessarily binding with the structure in a mandatory way. So they're kind of optionally there, and so the structure could still be standing without them. Like, you can remove an adjective noun, 30 minutes, or an adverb. So, these are like simple examples, right? So I usually mark with the star, examples of sentences that are not well formed, right? So, if you place something or someone, you need a somewhere. So the word to place calls for a, well, whatever would be in some, if your language of case is a locative or some well, anyway, somewhere, right? And so these are examples where you have a direct object, and you also have something else, like those keep someone busy, or but so this is specific to a particular verb, that it has this structure of necessarily binding with certain things. If you replace it with like a similarly structured verb, it might not have the same kind of roles that it calls. So in a sense, you can think of it as being the elements, the lexical items that you're using, that carry with them a certain information about things that they necessarily have to combine with. And modifiers, on the other hand, are things that are completely optional. They're not built into the structure, right? You can add some modifier, but you can add it or not to the sentence, and it doesn't affect the structure of the sentence. There's other notions that use, for example, specifiers. Normally they refer to things like articles, demonstrative and possessive adjectives, and quantifications, and these kind of things, the way to make the possessive phrase. And this of course already involve some specifically language-dependent rules. Some languages don't have articles at all. Some of them mandatorily require an article. Some sometimes do and sometimes don't. As English. And so on. So this is where there's different roles which are kind of existing in various languages, but the specifics then do depend on rules that have to do with particular languages. There is a more general sense for a specifier, which is a specific position in the sentence. So this is where the sort of slightly older terminology with this X-bar theory, where the internal vertices are labeled by specific roles within the structure, rather than with the new labeling that I described by the head. But basically, the specifier is whatever is in the sister position with the main head and complement combination.
So here is to think of it as closure. X bar, that's why.
That's right. Yeah, that's right. So it's yeah. So this is like this kind of completely unit of head and complement, and specifier is whatever is that, and acts as whatever type of sentence this is, like a verb phrase or noun phrase, or and right.
So just a question. I don't fully see how you define complement as something that needs to exist for the head to be defined as a complete entity.
Mm-hmm.
And then you said specifier is not a modifier because that also is mandatory in cases. So it seems somewhere like it's in the middle of the two, but then how exactly do you differentiate between a complement and a specifier?
Yeah, by their position, right? So in this it's because you have binary trees. So the terminology is that this spec head complement is whatever stands in this position with respect to the structure of the tree. So like that, if you think of it, it's like you have structures that do bind with the head necessarily for making a complete structure. But some of them they're kind of in different position in the binary tree with respect to where the head is.
Are you considering embeddings now?
No. This is non-planar, but even if this is non-planar, right? This is C commanding, right? And the other one is not.
And sorry, what does XP stand for? Is it X?
So in this terminology, the way one would just have X for different types of phrases, like something is a verb phrase or a noun phrase. Okay, so these are just like about the structure, like this, but the theta roles is something a little more specific. Now here you just say there's a head, there's a complement, a specifier that form the structure of your phrase, to which you can add modifiers. But basically this is the essential part of the structure of a phrase. But now you can be more specific about how these are combined together, like what kind of, and this is done more specifically by this idea of thematic roles. And you have a predicate, which in general could be a verb, but it can be a whole, it can be a noun, an adjective, and then this predicate has some argument, which again is like something that is required to complete its meaning. And the predicate then can take on like one or more arguments. One really defines this as the valence of the predicate, like how many arguments it has to combine with. And again, there's a distinction. So it's been in a sense the same idea, right? That we had for this phrase, this phases structure, that there are things that necessarily have to combine, and there are things that are optional. And in this theta theory sense, the predicate and its arguments are the things that mandatorily have to combine together. And then there's adjunctions that are things that accompany the predicates but are not necessarily required to be there. And so these various thematic roles, they specify in particular the number and type and placement of these obligatory matchings. So here's just some specific examples, right? So if I take the word likes, right, that has two arguments that it takes. It has there's someone that likes and there's someone that's being liked. And in the same sense, these are all similar structure where you have a direct object and a subject, and these are two mandatory relations. And there are other things like things like to put or to get. There's you put something somewhere. So in this case, there are three legs. There's the three trivalent. There's a subject. There's a direct object, and there's necessarily something that's locative and function. And adjuncts are things that are again not mandatory. Like it could be an adverb, it could be some sentence that qualifies what is happening with some additional information, and so it's another full structure by itself that's adjunct to the one that you are discussing, but it could be not mandatorily there. And so. Of course, as I said, some of these, depending on the amount of morphology that a language has, a lot of these thematic roles are absorbed into the morphology of the language by, indicating by different cases, different declension modification of nouns, which role is being played by that word. Yes.
So in this case, the verb to help looks like it would have valence too because someone helped someone else. But you could also say the old man just helped in general. So does help mean a different sense?
Yeah, that's right. So in some sense, there are cases where the same word can actually play different roles. So in that sense, you would want to think of that not as the same word, but your lexical items are decorated by something like this, and a part of it is this keeping track of what kind of valence they have, for example. So you could have like different possibilities, and depending on what structure you're building, you will use the one that has the correct valence.
Is there an example of valence 1 or something?
Yes, I mean, you could have, for example, if you have an intransitive verb, then, well, it still would require a subject. But yeah,
it rains.
It rains. Yeah. Okay, so what about now a little bit of mathematical background for this discussion? So an operad is a general algebraic structure. So here you could do it in a setting of various categories, but like let's just say in the category of sets. And so it's a collection of sets with labeled by positive integers. And you think of each of these sets as being a set of n-ary operations. So a set of operations that have n inputs and one output. And you have a composition law, which is the obvious one. Like if you have n inputs and one output, and you have n things, each one with one output, you can plug each of the output into one of the inputs. And you get something that has as many inputs as all the inputs that you had here. The inputs here are being saturated by these outputs. And so the resulting operation that you obtain has still this many inputs and one output. Okay. So you plug each output operation of this into the input operation of the other one. And you require some consistency of how to do this. And so you require an associativity of the operand composition. And also one requires that the this set with n equal to 1 contains a unit for composition. Right? It's acting as the identity for composition. So this associativity is actually easy to look at what it means just graphically, right? So it means that if you have like three layers of these this kind of operations, you can either do the first thing, which you plug in these outputs to inputs, and you obtain these two structures here, and then you do the second operation where you plug in these two outputs to inputs, or you do it the other way around. Like you first do plug in this, and then the other one, this should be the same. The resulting operation that you obtain should be the same. And then, okay, so this is the basic structure of what an operand is. And there is an additional property that sometimes the operand, so the basic definition of operands is just these compositions with associativity and the unit. And there's additionally, you can have operands that are symmetric, and you can have operands that are non-symmetric. If they are symmetric, there are two conditions that express this symmetry. So one is that, if you can permute, the outputs here, and as you plug them into the inputs, or you can permute the inputs here, and if you in the corresponding way, and if you do one or the other, the result is the same. And the other way is the composition. So this is just like computation on theta, and there's this other compatibility of permutations and composition, where again you first permute the inputs and you compose, or you compose first and then you permute the inputs, and this should be the same. Okay, so this is another very basic structure, and of course it has a lot to do with trees, right? Because these operations as with n inputs and one output, you can think of them as trees. And whatever happens in between your inputs and outputs, which depends on which type of operations you're looking at. And a related notion is that of an algebra over an operand. So again, we are in the category of sets. So an algebra over an operand is itself a set. So it's not an algebra in the usual sense. It's just a set. But it's a set on which your operations that give the operand are acting. So it means that you can use this set as inputs for one of these operations in the operand. So it means that if I pick something in the operand, this is an operation with n inputs and one output, I can plug in n elements from this set, and it will give me one element from that set as the output. And again, you want the natural composition property for this action that makes it an action. So it's like when you have an action of I don't know, an algebra on a vector space or something like this, the operation in the algebra should be the same as the composition of operations on whatever the algebra is acting, or a representation of a group. So it's the usual compatibility, right, between the internal operation of the thing that is acting and the action. And so in this case, again, you have the composition inside the operand and the action on elements of the set. And this is the associativity of the composition inside the operand applied to with each operation applied itself to. So you either compose in the operand and then apply, or you first apply and then compose in the operand. That's okay. So that's yes.
Go back to the previous slide where you showed the symmetric condition.
Mm-hmm.
Are all of these conditions equality or up to natural isomorphism?
Sorry, are all of these conditions?
You're demanding that it's exactly equal or isomorphic?
So yeah, of course, this depends in part in what category you're looking at operads and whether you want to allow, you know, just this up to isomorphism in the category, or you know, of course, yeah, sometimes just to say what it means to things to be the same is not a natural thing to do in a categorical setting. The natural thing to do is to require that they are isomorphic. So that's but okay. Yeah. Okay, so coming back to our setting, where does one, how can one see this kind of structure? Right? So we were, you know, discussing, so syntactic objects are these binary rooted trees where the leaves are decorated by these, you know, lexical items with their syntactic features. But I can also form there is also an operad that is freely generated on a single commutative binary operation. So like we generate the magma of the syntactic objects, right? But now we can just generate these as operations. You know, just all the possible, you know, compositions that you can form from these binary operations, iterations of this binary operation. And of course, you can think of these as just being, again, binary rooted trees, right? But not with nothing labeled anywhere. They're just binary rooted trees where whenever you have an internal vertex, it means that you are applying once this operation. So they are templates for how you apply, you know, the structure of the tree is telling you the order in which you are applying this same operation over and over again. And these clearly form an operad because, you know, you can compose these various. So if you have a certain sequence of applications of this operation in a certain order, and you can put that, or compose that with another such, you know, combination. So in exactly the same way as this operand composition works. And the thing is that now you can see that the syntactic objects that we have constructed are indeed an algebra over this operand, because if you have one of these trees that has nothing, no labels at the leaves, right? And you have a bunch of trees with labels at the leaves, you can plug them into each of the unlabeled leaves of the other one, and you get a much bigger tree where now all the leaves are labeled. So it's like saying that if I have one of these operations, and I pick n syntactic objects, I plug them into this, and I'm going to get a single syntactic object where the leaves is the union of the leaves of these ones. And the structure is determined by which operation I've chosen here and which syntactic objects I've chosen. And so I can think of it this way, that you have, you can think of the way of assembling together syntactic objects into larger ones that is based on this operad action. Okay. So of course there's a small subtlety here, regarding the ordering of leaves, right? Because we are dealing with trees that are non-planar. And so when I said that, when I described this operad composition, I said, well, you know, you plug in, if I give you a sequence. So I mean, when I describe it like this, right? I'm saying, okay, I have an output, and I'm giving you an ordered sequence of inputs, and I'm plugging in this first one to the first leaf, and the second one to the second leaf, and so on. So of course, if I'm numbering the leaves, I've planarized the tree, right? And so, but which I don't want to do, because I want to keep my trees non-planar. So I have to kind of, keep track of that, in the sense that, okay, I have, the set of leaves is well defined, and the set of leaves, and you assign a certain grafting procedure to when you have to you decide the way in which you plug in to where, and then you decompose the associativity to keep track of what you plug in where, but without necessarily using this as so it has to be like you have to decide like well, you have to decide some labeling that distinguishes one leaf from another so that you can see what, but it doesn't necessarily have to be an order set. Okay. And then, yeah, you can write everything, including the symmetric action in terms of action on this set of leaves, but without necessarily making it an order set. I mean, there's nothing. You just identify, the set of symmetries of the set with a copy of the symmetric group. But okay. So this is just a small remark that one wants to keep the trees not endowed with a particular choice of planar embedding for the moment. So one thing that also one wants to keep track of is the fact that we already had some constraints about whether you can put a head function or not on these trees, because these are like some of these constraints that you want to have anyway, regardless of a specific language dependence. And so you want to somehow keep track of this also if you think of these operations where you plug in your syntactic objects into this kind of operand structure. So if you have a head, so if you assume that the trees that you're dealing with come together with the choice of a head function. So a head function is, say, one thing that selects a leaf from wherever you are inside the tree, like with the rule that if you have a subtree, if the head of the larger tree goes into the subtree, then it has to agree with the head of the smaller tree. So if you have pairs of a tree together with the choice of a head function on that tree, then this operand composition will still give you something that has a head function. And this is just exactly because of the property of the head function, because if you are in the structure above where you plug this thing in, every leaf has its own projection of which it is the head. Some of them don't project any further, some will project to somewhere. If I plug in another tree, well, whatever was that leaf, it will go to the head of the tree that I'm plugging in there. So if that leaf stopped there, that would be the maximal projection of the head of the tree that I'm plugging in. If it goes somewhere above, that would be the maximal projection on the entire structure. So this is kind of compatible with the property of being a head. So you can, if you have assigned heads, then they do combine well with respect to this operand composition. Okay, so now in what sense is this point of view useful to think in terms of these theta roles and theta theory? So in a sense, one way to think about these theta roles is the fact that when you combine things together in your structure, the theta roles have to match. So if you have a predicate that is calling for a certain kind of theta roles, whatever is combined in the structure directly with that predicate has to have the correct theta roles. So this is something that in this setting of these operand compositions can be incorporated as a condition. And I'll say in a moment how you do that. I just want to make first one comment about this theta role matching of this matching of theta roles, which is that in linguistics one talks about, well, it's usually called, if you look at the papers in linguistics, it's always usually called the duality in semantics, and So duality is, I think, from the mathematical perspective, maybe not the best term to use because it suggests something that is an involution. It's really more like a dichotomy in between the role that external merge and internal merge have. So the way it's usually stated is that external merge is responsible for this assignment and matching of theta roles. And internal merge that moves structure around does not affect the theta roles. So it doesn't create new theta roles. It doesn't require matching of theta roles. So in linguistics, these are usually called the propositional domain and the clausal domain. Propositional domain is exactly the building of the propositional elements that have to match. So it's these constraints about what mandatorily have to bind with what in what way. And the clausal domain is more like what it's also called non-argument structure or information-related structures that allow you to like change certain meanings by moving parts of structures, but it doesn't affect this assignment of roles. And in a sense, I'm mentioning this because I'm arguing now that these theta roles and theta theory can be described or can be encoded into something that has to do with this kind of operad structure. And this operad structure has directly to do with the building of syntactic object, and that is external merge. It's not internal merge. So it's compatible with the fact that you want the theta roles to be entirely something that's only has to do with external merge and doesn't involve internal merge at all. Okay. And so the notion that one can try to adapt to deal with this idea of this matching of theta roles is called the colored operad. So in a way, this is something actually very simple because it's the same idea as when you pass from a group to a groupoid. In a group, every element multiplies with every element with no conditions. In a groupoid, two things multiply, only they're like arrows. So they compose only if the target of the first arrow is the source of the next one. So there's a compatibility of something that has to match. In the case of a groupoid, is like target and source. Yeah. And so there's similar things. You can go from groups to groupoids to semi-groups to semi-groupoids, ring to ringoids, semi-rings to semi-ringoids. We'll meet some of this stuff. So fortunately, the terminology operadoid never made it into the mathematical literature. Such things are actually called colored operad. In fact, you could call a groupoid a colored group. But the idea is that you have matching conditions, and these conditions are labeled by colors. Just means that you have to have some matching data in order for composition to occur. So in the case of an opera, instead of saying that you have, so your legs are now colored. So instead of having like a ON, which is just a n inputs operation, you have with n inputs and one output, you have an operation that has an output with the color C and inputs with color C1 and Cn. And when you do the composition, you want that, if this is the input to which you want to plug in this first output, the colors have to match. And so anytime that you do one of these this plugging in of two legs, they have to have matching colors. And you write the same kind of associativity condition, but everywhere the colors have to match. So this composition happen if and only if there is this matching of conditions. It's exactly like the composition in a groupoid happens, so only if the arrows are the same, pass through the same target and source. And now, of course, when you require that there's a unit for composition, now you have a unit for each color, right? Because that has to plug in the right one. So in a sense, you don't really think of it this way, right? I mean, this will not be a good composition in my colored operad because I have a mismatch of colors. This would be a good composition in my colored operad. And so, that's the idea. In a sense, you can think that, when we are trying to build a structure that involves these theta roles, if you have a predicate that is, somewhere in your structure, this emits colors on the edges that will bind to the rest of the structure, and nearby, structures that mandatorily combine with that, they will have to carry the same color. So in a sense, this theta theory is some kind of like a coloring algorithm on your binary rooted trees that will have to match. So you can think of this as being another constraint on your syntactic object. So in addition to these constraints that you have head and complement and phases and labeling of the internal edges, you also require that there is a coloring that works with respect to the theta roles that are assigned to the predicates in your structural formation. Also, when you choose your lexical items, some of them will come with these required colors, and this have to match. Okay. So this is the idea. So you now have a set that describes the theta roles. They're labeled as predicate. So both predicates and arguments have their theta roles. There could be these various things. Agent, locative, instrument, possessor. The standard labelings for theta roles are used. And you have a syntactic object that have to have a head function, which is already a filter that we've used. But in addition to that, they have to have these carry these colors that have to do with what data roles they are involved. And this operand composition now will have to be compatible both with the head and with the colors of the data roles that are assigned. Okay, and this, as I was saying, is involving only the external merge as checking of the theta roles, and not the internal merge as is required by the linguistic theory. Okay, so the other thing, so this is for the theta theory, and the other thing that I wanted to say a little more about is obligatory control. So I'm going to use an example from Chomsky's book on merge and strong minimalist thesis. So suppose that I just look at a simple sentence like this. The man tried to read a book. So this is the syntactic object that carries this sentence. So it's obtained by a sequence of merge. These are the building process for the structure. And so if we think of it in terms of this structure that I just said, we can view it as having one of these elements in this operand that have slots into which you can place things. And for example, I can plug in so let me just first do it in this way, right? So I start with this, and I plug in these syntactic objects in these different slots. And now I'm doing it in this way so that I'm plugging in this syntactic object both here and here. Okay. And in the sense that I have a substructure which reflects this kind of complete phase, the man reads a book, and that's like a complete substructure. And then there's another one, which is like the man tried, which is a complete substructure in itself. But now these two are bound together into a single structure, where I'm also imposing a constraint, which is that these two roles that the man has in this sentence have to actually be identified, because it is the same. Well, it's not just, you could have sentences in which the same syntactic object occurs with two different roles, but here you are actually marking that it is the same. And
is there a reason that you wanted to be a complete substructure? You wanted to say the man read a book,
Yeah, so because I'm gonna try to build it as like complete substructures that that are combined together into a larger structure. And so I can, right, I didn't think of it this way. Right? I have this substructure, and I have this substructure, and I have this way of combining them together into this larger structure. But now, I mean, the point is that, if I, for example, if I just say a different sentence like the man saw the man, okay, so I still have the same syntactic object that occurs twice, but here they're not identified. I mean, they're not the same, the man. But in this, when I combine this, I'm also implying that these two are in fact the same. And in fact, ultimately in your form sentence, one of these will disappear. Right? In your form sentence, this will not be externalized. What will be externalized will just be the rest of the sentence. And this is part of the fact that these two are actually identified as a single structure. So they're no longer independent accessible terms that can independently moved. They are actually restricted to lie, say, on a diagonal. So they are actually identified. So if one moves, they move simultaneously. And that's why, that usually what happens in this case, as it happens with the internal merge, the deeper copy gets canceled. Doesn't get externalized. Okay, so this is the structure. So you start with something like this, where you plug in things, but now the things that you plug in, ordinarily would come just from this. It has 6 inputs, so you can plug in six syntactic objects to that. But now you're really plugging in 6 where they lie on a diagonal, or 2 of them are actually the same. Right? So this you have, so you can this possibility of considering sub diagonals inside your space of inputs for these operations. And this is what they usually refer to as a form copy in the linguistic literature, which is exactly to say that 2 items actually have to lie on a diagonal. And so this is this different from saying that your forest of your workspace can have the same syntactic object occurring several times. That's referred to as a repetition in linguistics, but they don't necessarily have to end up playing the same role, being the same identified elements in a sentence. And so the point with this is that if you are really restricting to a diagonal, then when you extract substructures with the coproduct to use for internal merge, then you no longer extract these separately. You either extract it once from everything or not at all. So
what's the hat?
Sorry?
The hat.
Yeah, so it means you fix one object and you require that several of them are identified with that one. Yeah, I mean you could say, I don't know, like Ti equal Tj, but no, just to say that you can have a certain set of elements that are all equal to the same one. Yeah, so some chosen one that you want to use for. And okay, so in particular, it means that if you are in one of these situations where you have some of these obligatory control structure, then your co-product, when you want to do movement, is extracting on the subforest that either contain all of these copies at the same time or don't contain any of them, but you cannot like extract some of them and leave some of the other. And this is just, this is still compatible with the properties of the product, but it takes into consideration this type of constraints. Okay. Yeah, so this is again from the same example. You have the result is that when you extract, you just extract all of them at the same time, and the deeper copy gets canceled so that you don't externalize it in the end. Yeah, whereas if you just have repetition, like say many people, these are not the same many people, so each of them remains accessible independent of the other for further movement. Okay, so this is like everything that has to do with this general pre-externalization structures that you have. Now, I mean, externalization is what models the actual diversity of languages that we see. I mean, because everything that happened so far is, I mean, the examples you can choose from one language rather than another, but it's the structure is designed to be universal across languages and just capture the essence of what is the sentence formation. And now I think I gave this example at the end of last time with this again this cross serial dependencies, and that illustrates how there are two different kind of things that you need to do when you try to embody this general mechanism into a particular language. And one of them is the fact that now you have to choose a certain word order for your sentences. They're no longer these non-planar trees. They have to become planar trees. And so you're going to have to lift your non-planar trees to planar trees with some choice of sections or choice of planarization. I'll say more about this in a moment. That is language dependent. And the other thing that I was showing with that example is that among several structures that you can build from the same that involves movements, with different kind of movements on the same structure, some of them will be useful in the language, the specific language they're looking at, and some of them will not. So you will also have to eliminate. So since we have already eliminated structures that are ill-formed in general because they're not parsable, they don't have a head and so on. But now there's also structures that in principle are fine from that perspective, but that you don't want to use because they will not correspond to the way to some constraints on how the sentence is structured in one particular language. So you have basically two operations. One is this planarization of the trees, and another is like a big quotient map that kind of kills off everything that is still non-viable for the constraints of one particular language. So both of these operations are now language dependent in a specific way, and the question is how to model this in a way that captures the diversity of phenomena that one sees in different languages. And
so what exactly is big bang by error constraints, you say? What object is that denoting?
So for what you got here, or what you?
I'm saying the projection. That's the bisymbol, right?
Yeah. So I'll come to discuss this now. Yeah, that may get this. Yeah. So first of all, let me just discuss this and the section. Then I'll discuss what happens here. So in a sense, well, one can think of this two-step procedure like from the mathematical perspective is a general example of a correspondence as a way of mapping two things. Like in general, you don't like have a directly map here, but you kind of go to something that maps down to both things, right? And so I'm going to just try to go through the various parts of this picture and explain more in detail how they work. So the first thing is this, right? We have described the formation of the syntactic objects as these non-associative commutative magma generated by the set of lexical items. Of course, you also have a free non-commutative, non-associative magma where you don't even impose this commutativity relation. In this one, the only relation that it has is the commutativity of the operation M, which is the non-planarity of trees. But if you don't even require this commutativity, you have this free magma where that generates the planar trees. So these are all the planar binary rooted trees with leaves decorated by the same set. And now, I mean, I'm going to use this notation in the sense that it's a tree together with a planar embedding. And now, I mean, so in this planar setting, this merge operation is this non-commutative merge operation. And there is a projection from this magma of planar binary rooted trees to the one of the non-planar binary rooted trees that just forgets about the planar embedding. And this is a morphism of magmas. It just kills the commutators. And this is a canonical map. It's not dependent of any choices. It's just forgetting the planar. If you have trees together with a planar embedding, you forget the planar embedding. You just keep the trees, and it's compatible with this merge operation. So it's this map is very nice. It's a morphism of magma. It's completely canonical. It doesn't depend on any choices. There's a problem though that it goes in the opposite direction with respect to what you want to do. You actually want to planarize tree. You don't want to forget the planar embedding of trees. Okay, so and the problem is that if you try to go the opposite direction, there is no map that is as nice as this one. There's no morphism of magmas that would go the opposite direction, because if you are mapping from a commutative magma to a non-commutative one, you would have to go inside a sub-magma that is itself commutative. Otherwise, there's no good way of doing this mapping. But this free non-commutative, non-associative magma does not have any commutative sub-magma, because, well, you can easily see that if it had one, if there were some actually non-empty trees that would be in this commutative submagma, then its product with itself would still be there. And you can see that if you start composing product, is not the same planar tree anymore. So it's manifestly not you cannot have any commutative submagma. Okay, so it's like you're trying to take a one-way street the opposite way, and there's a problem. Well, I mean, okay, you take a one-way street the opposite way, you pay a fine for doing that, but you can still do it. So the fine that you pay for doing that is that A, this is no longer a morphism of magmas. B, it's not canonical. It will depend on choices, right? So what you're doing now, you're taking a section of this projection. So you're choosing, well, the section of projection is just by definition something that composed with the projection gives you the identity downstairs. Okay, so it means that it's a choice of a point in each fiber of the projection. So indeed, a choice of a planar embedding for each tree. And well, at the level of linguistic consequences, these two properties that you lose are exactly what you expect to get, because it's not. So the fact that this choice of planar embedding is not a morphism of magmas, it's really telling you that the structure formation of merge can either happen before externalization or after, but not both of them simultaneously and compatibly. Right? So in this model, all the structure formation is happening before externalization. And once you externalize, you're not trying to do the merge operation again, because you can no longer do it compatibly. Right? The older formulation of minimalism had all the structure formation happening after externalization. And that required all this kind of domain checking and so on, which I'll talk about more later. I'll talk more about the explicit comparison between the two models. But we see that somehow you cannot have it both ways. you can either have it one side or the other, but this is not a morphism of magma, so you cannot make it happen simultaneously and compatibly on both sides of the externalization. And of course, the fact that there's no unique, choice independent, unique, section independent of choices, is just the fact that this is going to be necessarily language dependent. There is no like language that most closely resembles the way that the human mind thinks, not even French. So it's those. I mean, these are two natural things to expect that this section should have, and in fact, no, they necessarily have this way. Okay.
So the first step is almost like to externalize a language, you fix a gauge. So
yeah, exactly. It's in a sense that you're exactly doing like you have this symmetry, right? In the structure formation process. You have this symmetry with respect to all these permutations that would change the planar structure without changing the structure of the non-planar tree. And now you're like fixing a gauge by choosing one of them. But exactly like when you fix the gauge, you're making some choice that is not canonical. Okay. So how does one do this? So the point is that you can do it in whichever way you want, as long as it does. So its language dependence is here, just capturing the fact that different languages have certain kind of word order rules. Right? So some languages are much more strict word order rules, and some of them are slightly more flexible word order rules. Some languages are very flexible word order rules. And this, of course, correlates a lot with whether a language has a lot of morphology or not. Because languages that have noun declension, they tend to have more flexible word order, because in a sense, the fact that the word in itself carries the cases that tell you more directly what it was binding with what, means that even if you place it somewhere else, you know where it was supposed to be, right? So in some sense, your flexible word order is a way of saying that you remember the actual structural relation, even if your words are slightly scrambled, right? But the word is really, in some sense, built into the morphology of the words. And sentences that don't have languages that don't have morphology at all, they tend to have a very rigid word order structure. But even languages that have fairly flexible word order structures, they tend to have a preferential word order structure. Like, for example, among the Indo-European languages, Sanskrit is the language that has the most flexible word order structure. It's also the one that has the most flexible morphology, the most rich morphology in terms of like number of cases. It has more than any of the other Indo-European languages. Most of the other Indo-European languages have gradually lost some of the cases, replacing them with preposition and stuff. And but even in Sanskrit, there is a preferential word order, which actually happened to change historically over time. Historian of linguistics, historical linguists tend to think that is by interaction with the Dravidian languages that had different kind of word order structure. But in a lot of classic texts, you have, for example, tend to have verb last. You say "Kalo as me," Kalo, or also to quote Oppenheimer's favorite Sanskrit quotation, and things like this. So even when you have a fairly flexible word order, you have preferential word orders, and so and this is learned by exposure to examples from a language in the phase of language acquisition. You are exposed to word order in particular. So your choice of planar embeddings have to somehow not violate word order. This still, in some cases, allows for some flexibility in how you make this choice of a section. Because it just has to not violate your constraints. And then, okay, so this is whatever makes this learns, so something in the process of language acquisition to learn the embeddings, the planar embeddings.
Sorry, two questions. So,
yeah.
Firstly, when you talk about this planarization, so you've been using binary trees with examples in English, but just to be clear, if you had declensions in nouns, you would still put it in that internalization.
Yeah, so if you add declension in nouns, so the idea about morphology is that more and more people want to think of that as really being part of syntax, which is absorbed inside, the formation of words. So, for example, like if the difference between a language that has noun declension and a language that does not is that the same structure is in a language that does not is usually built by attaching a preposition to a noun. And so if you attach a preposition to a noun, that is a certain substructure that gives you, a phrase that has a combination of a preposition and noun in a certain tree structure. If you have a case that modifies the word in a language with noun declension, that you think of it as being a leaf of the tree. But if you explode that leaf of the tree, if you blow it up, it has structure inside. And the structure is again this structure that takes the case and the root of the lexical root and combines them together. So in a sense, the point is that, so at the very beginning, right, I make this observation that languages like many different scales at which you can look at it. So when you think about syntax, it's sort of the large scale structure of language where the unit of measurement are like sentences, but morphology is like the scale at which the unit is the word. And then you further have phonology that kind of breaks up words into their compounding sounds and sound systems. But it's like you can zoom in at a lower scale. And the morphology, when you zoom in at a lower scale, it kind of looks like syntax again, in the sense that you have the same kind of structure. And even phonology, there's works, even very recently that use the same formalism of merge and to describe phonology, how units of sounds combine together to form sounds of words. So that's basically, I think, in general, how one treats the difference between languages that have noun declension and those that don't. It's like you sort of blow up that and you see it as a structure in the same way as syntax.
So you can write it down and nothing breaks. It's perfectly consistent if you add this kind of granularity and then you try to do this kind of externalization. It can all handle, even if it sounds like this is the edge case of, you're talking about syntactic merge and now you start thinking about morphology. So this is able to handle that, or?
Yes. So you're right that in a sense, when you do this choice of planarization of trees that account for compatibility with word order rules, if you add morphology, you would also, for example, some languages tend to have morphology that works more with prefixes than with suffixes. So it's again a kind of word order structure in there. And so that would still be, once you blow up that scale and view your morphology itself as trees with structure, that would also be an assignment of a planar structure to those trees. So you can take this viewpoint down to the lower scales as well.
So is there a reason that you had to split this into two steps? Because in the languages where you do have declension and reduction and so on, it doesn't make much sense to have planar embeddings that just are nonsensical. So is it because it was more convenient mathematically to
So, well, yeah, it is in a sense more convenient to think of it as two operations, but also, there's there are two such different roles that rules of syntax in different languages have. They're not just about fixing word orders, right? There's some other, I'll say a bit more about syntactic parameters, which are the way that linguists try to give coordinates that describe different properties of syntax. And some of them influence word orders, but some of them don't. like, of course, it's a bit, this is a bit of an oversimplification because sometimes, I mean, there are a lot of relations between these parameters. So some of the parameters that don't necessarily apparently have anything to do with word order can still, to some extent, influence word order. So it is indeed a bit of a simplification to separate these two. But for example, no, some languages have a pro drop and some don't. So in some you can drop the subject or of a sentence, and in others you cannot. Like it rains in English, but in Spanish you can say llueve and then drop the subject. And so in some languages you can do it, and some languages you can't, and it's a 0-1 thing. And this by in itself is not a word order property. It's just something that says that certain structures are viable in that language, but not in another language.
But isn't it right to say that's more fundamental than word order? I mean, the reason I'm asking this is if you have these constraints, then that should emerge from that, right? Word order is something that, like what's more fundamental is the rules of your language, and then that will allow some word orders and will not allow some linear embeddings. That should.
Yeah, but word order is also a specific property of your language, right? Because it can be different in different languages. So in a sense, the point is that these are all characteristics that are language specific. There's no like common word order. Like for example, I gave this example of the relative position of subject, verb, and object, like across world languages. There's a lot of languages that are SVO. There's a lot of languages that are SOV. Then all the permutations are represented. Some of them are very rare. Some of them are very common. But still, all of them exist in as the preferential word order in some languages. So it's it is something that's language specific and that is learned. It's acquired in your process of language acquisition. So but indeed, this sort of it's slightly different, from other syntactic parameters in the sense that, this word order, you're right, that there's no like a default setting for which some are changes an exception, right? Because okay, all of them could be represented, and there's no reason why one of them would be like a more natural default, and or like one of them would be the ground state, and the other would be like the excited states, right? They're all somehow equivalent, right? But other syntactic properties, in a sense that it's more natural that like they have a default, like something is possible in a language, but in certain languages it's not possible. Or and that's linguists that study syntactic parameters, they tend to make this distinction between certain kind of syntactic parameters where there is a natural default of what should be like the ground state. And then there are languages that differ in that default. But others, especially word order ones, don't have a default. And like all the possibilities are somehow equivalent on an equal footing, but different languages do have a preferential one. So in a sense, you're trying to like make this distinction, which probably has some distinction also. I mean, of course, the specific method by which the setting of these parameters when one learns a language happens is not known, in the sense that it's not well understood what is the actual neuroscience correlate of these of this phenomena, these processes. So of course, there's a lot of empirical evidence that people observe by looking at how children learn when children that are learning a language, and the process by which that happens. So there's a lot of data, empirical data on that. And but no, it seems likely that the process of setting the parameters for these two different kinds of parameter might be slightly different. So that's one reason for like trying to have a model where these two are treated as slightly different steps. And okay, so there is this lifting of your non-planar trees to the choice of a particular language-dependent planarization. And then there is this quotient map that just eliminates things that are not viable in that particular language because they violate certain other language parameters. Like the example that I was discussing at the end of last time with this cross-serial dependent structure in Dutch, you have to make this verb rising movement twice, using an internal merge to get to the right cross-serial form. And so of these different forms obtained from one another by internal merge, Dutch would externalize one of them, English would externalize another one, and for example, German would also use only one verb rising operations rather than two, so it would externalize it in a third different way. So there is simply that you have all these structures available, but some of them are dropped and some of them remain. So it's like you have a filter that is language dependent that says of these ones, these ones are not viable, these ones remains. So that's more like what this quotient map looks like.
So then really the language specific part comes in for the second step. Right?
The language dependent?
The first step you're just lifting, and then you haven't added any language specific.
That's right. So, well, you can lift it. So you lift it in a way that doesn't violate your word order parameters of language. Of course, you can lift also things that will eventually be killed by this quotient map. It's just that, okay, you simply planarize everything as long as the way you planarize it does not violate the word order structure of the particular language that you are. But this still allows for a lot of additional freedom that gets filtered out again.
So there is language dependence in the choice of lift also.
Yeah, that's right. Because again, it's that a particular language will have a preferential word order. So you try to planarize in a way that doesn't violate the word order structure of that particular language. Okay, so in a sense, if one thinks of it this way, you're basically saying that you have this type of correspondence structure. You have these planar trees, planar binary rooted trees that account for everything, and on one side it projects down to the non-planar one with this natural non-canonical morphism or madness. On the other hand, you have this quotient map that goes to that inputs the filters of the particular syntactic parameters, and so you think of it of climbing up one of these arrows and going down the other one. So in general, I mean, this is something quite natural, right? There's a way to think about how to map objects. I mean, there's many settings in mathematics where the natural way of mapping objects is not as functions from X to Y, but as something that covers both X and Y, and that you transfer things from X to Y by pulling them back here and pushing them forward. Yeah. So you think of this as a way to transfer structures. This happens very often, right? In geometry, you can, for example, you have structures like vector bundles with spaces of functions. You pull them back to some other covering space and you push them forward on the other side. Sheets, whatever. So in general, if in a categorical setting, if you have a category that has pullbacks, you define correspondences as one morphism in a two category of spans over your category C. And so in the two category, you have objects and one morphism and two morphism between the morphism that compose either following the composition of morphism, one morphism, or transversely to it. And so in this setting, you have objects of your category. One morphism are correspondences of diagrams, and composition is given by pullback of this. And of course, so the general picture that you meet in a lot of other places in mathematics is that you have a kind of correspondences of spaces that are of this kind. So usually something like either something that projects or something that is like a subspace of the product of X and Y, depending on the setting. But so there's correspondences at the level of spaces that are spans in this sense.
So
and
these are one morphisms.
Yeah, so these are the one morphisms. So these diagrams are one morphism, and the two morphisms would be morphisms that relate two of these comments. Okay, so the reason why I'm discussing quickly this categorical perspective is that in general when you so from this linguistics perspective where does this fit, right? So we're seeing that this construction of externalization as a correspondence is dependent on one particular language, and in general when people want to study language variation in the sense of how syntactic structures can vary across languages. They want to compare these between two different languages. So it is like saying, okay, I have two of these correspondence diagrams. I want to compare them. And this will exactly be the two morphisms of this category that relate to two of these diagrams in a compatible way. So in a sense, what one wants to see as what is the set of your syntactic variations is what is what are these one morphisms and the two morphisms between them. Right? That's one way of thinking about this problem of describing the space of available free domain syntactic variation.
So I remember in the very first class, someone asked if there's a notion of homotopy between languages. This is the notion of homotopy between syntactic.
Yeah, in a sense, that is exactly what this should represent, right? This kind of morphism would be, a way of like going from one to the other. Well, of course, it's one can argue that because these are discrete structures to some extent, so the variation is on discrete points. So you don't have like homotopies in a continuous sense, but you can have in morphism in this sense that can give something like analogous to that. So, I mean, so in general, if one has this span picture for spaces and one thinks in terms of algebras, the correspondences would go the other way. But of course, you can also have like what refers to as co-correspondences, where at the level of algebras, the arrows are this way. So I'm saying this because in this setting it looks more like these spans, these co-correspondences in the usual categorical language. And the reason is the following: that if I want to write this out as a correspondence in this sense, I can I want to build into my correspondence the merge action, so that I can also keep track of how things are formed and then externalized. Right? And so if I want to look at so let's say I have my magma of syntactic objects, and I take the vector space spanned by that. The operation is non-associative and commutative. So I get an algebra which is non-associative and commutative. Okay, dealing with non-associative algebra is a bit of a pain, but this just means that the corresponding representations are just a bunch of linear operators, right? They don't compose according to the usual representation composition because the algebra is non-associative. So, but this just means that you can encode your merge action. Like if you, okay. Okay, let me just say this to finish. If it's the same thing as looking at like all the action of the merge on your workspaces, and for all the possible ways in which you can apply your actual merge, and fix in all possible ways one of the two arguments of merge and look at the action of the other one as a representation of this non-associative algebra. So you can, to an extent, just recover the same picture of the action of merge on the workspaces in terms of this kind of objects, which are these non-associative algebras and the corresponding action vector spaces. And this gives you a picture of this externalization correspondence and how, to what extent it can keep track of the action of merge or not. And as I said, you cannot. This goes back to this thing that you cannot have merge simultaneously and compatibly act before and after externalization because you're trying to climb this morphism of magma in the wrong way. But so what will happen is that necessarily if you try to define merge after externalization, it will only be partially defined. And that's exactly goes back to the formulation of the older form of minimalism where all these merge operations were partially defined on domains that you need to check compatibility of. Okay, I'll continue next time. Yes.